which will be given by Gianluca Iori. Gianluca Iori holds an MSc degree in mechanical engineering from University of Bologna, Italy, and a PhD from the Faculty of Process Sciences and the Technical University Berlin, Germany. From 2013 to 2014, he was a research fellow in the computational bone biomechanics at the Medical Technology Laboratory of Rizzoli Orthopedic Institute in Bologna, Italy. Between 2015 and 19, he was graduate student at the Berlin Brandenburg School for Regenerative Therapeutics, where his research was awarded with grants by the German Academic Exchange Service (DAD) and by the Harvard University Hospital, Berlin, Germany. His research focused on imaging and on the mechanics of nature materials. Since 2020, he is appointed as Beamline scientist at SESAME, where he is coordinating the design and construction of synchrotron beamline for X-ray tomography within the European Horizon 2020 project BEATS. The title of Gianluca's presentation is BEATS Tomography Beamline, Design, Construction, Operation, and User Possibilities. Gianluca, go ahead.
Good morning, and thank you very much for the opportunity to present to INSC. Thank you, Dr. Akhtar, for the invitation and to the organizers. So the talk that I will give focuses on the technical description of the beamline that we are designing and constructing at SESAME, and on some of the scientific applications that can be tackled with it. So this is the layout of the presentation, and first of all, I will describe generally the layout of the beamline. I will then quickly go through some principles of computed tomography to show the properties of the X-ray beam that we are expecting, the ways in which we will operate the beamline, and then I'll go very quickly through the equipment that you will see when you come as a user for beam time at BEATS. And this is the first half of the talk. And then I'll go through scientific applications and possibilities, in particular in three ranges of applications. So there is health and biology, material science and engineering, and then geology and environment. I leave archaeology and cultural heritage to a better speaker for that, Dr. Kirsi Lorenz, who will talk after me. So this is the layout of SESAME. My colleague Andrea Lausi showed you already this plan. BEATS will use an insertion device which will be hosted in a short section of the storage ring here. One thing that you see from the layout is that the storage ring is not in the center of the building, is eccentric, and you see where BEATS will be hosted. This is to make use of 45 meters and have in this way as long as possible imaging beamline. We will see why it is very important to go far from the source for some of the applications of computed tomography. So 45-meter long in a short section. This is the layout, the general layout of the beamline. So it is divided in a front end on the left. This is, you see the wall here. This is equipment which is inside the tunnel of the storage ring of SESAME. There is then right after the tunnel an optics hatch which contains the monochromator of the beamline, and then there is long pipe shielded with lead that brings the X-ray beam to the experimental hatch, which is also a quite long, 14-meter long hatch, also shielded for the experiment. This is also the layout of the beamline, but a schematic layout, and again, you see the total length. I'm looking at the picture now, 45-meter long beamline. On the left, there is the source. In the front end, there is equipment to absorb X-ray radiation that we don't want, we don't make use of. At 9 meters, we have the first window. It's a diamond window separating the ultra-high vacuum of the accelerator from the high vacuum of the beamline itself. And the last equipment that I'm showing here in the front end are filters. These are used to tune the energy, particularly to remove the low energies when we want to operate at high energies, at high photon energies. After the wall, there is, as I said, a monochromator, which is a double multi-layer monochromator. And you see already two of the modalities that we can actually target with beats. We have a pink beam, which means the monochromator is removed from the beam path, and we allow the whole X-ray flux to reach the experimental hatch. This is done when we need a high flux and we need fast experiments, so a lot of photons. When, on the other hand, we want to tune the energy for the experiment, we use the double multi-layer monochromator, and with a certain offset, as you see, which will vary between 6 and 16 millimeters, and bring the monochromatic beam in the hatch, in the experimental hatch. So down here at 30 meters, from 30 to 45, we have slits that will tune the size of the beam impinging on the sample. There is a second window, after which we are in air. There is the sample with a manipulator that I'm not showing, and a detector. I will show more in detail what this is. But the message here is that we have already two modalities, a white beam mode versus monochromatic beam mode for selective energies. And the important thing in this case is to have a high flux to see through large, dense samples. And this is why my colleague Axel already showed you that work package 3 was actually responsible for designing and taking a decision regarding the X-ray source for beats. This was taken in September last year, and work package 3 decided to adopt a 3 Tesla 3-pole Wiggler design. So it is essentially one big pole surrounded by 2 auxiliary poles. In this way, the source can be installed in a straight section of the accelerator. And this is a simulation of the flux that we will have. In red, there are 2 beamlines, SESAME at the Elettra, the Italian synchrotron, and Topotomo at former ANCA, now is CARA facility at KIT. These are 2 bending magnets, imaging or tomography beamlines, and you see that installing a 3 Tesla 3-pole Wiggler, we will reach higher photon energies. In blue, there is a comparison with Tomcat at the Swiss light source, which is a bit the example that we are following. So a significant increase in photon flux at the high photon energies with respect to a bending magnet. And of course, a direct impact on the scientific case, because it allows us to access and study a larger variety of samples. Now I will spend a couple of minutes on the principle of computed tomography. I must say here, I'm very sorry for the part of the audience who knows this, because this is what I'm gonna show is very basic, but I need this for what comes later. So the picture is shows the first CT scan that was introduced in '71, is the AMI scanner in the UK. And for this invention, actually 8 years later, Godfrey Hounsfield and Cormac won the Nobel Prize for CT in 1979. How microtomography at a synchrotron laboratory looks like is actually very different. This is a picture from Tomcat. So this is a micro CT beamline at the Swiss light source. The X-rays are entering from the left. This is the X-ray path. There is a sample manipulator here in the middle, and on the right there is a microscope. And you see already the length of the experimental hatch, allowing to tune, to modify the propagation distance between the source and the sample, as well as between the sample and the detector. So how this works is very roughly in this way. The X-rays come in, they are parallel X-rays come in and hit the sample. After passing through the sample, they hit a scintillator. In fact, what we record is visible light, which is converted from X-ray by a scintillating screen, which is at the entrance of the microscope here. After the scintillator, there is an objective lens, a light microscope that focuses the image on CCD, like in the diagram, or as CMOS. Actually, technology has evolved already, and we are working mostly with scientific CMOS sensors. The image, the projection image, is taken at different angles of the sample, and this is a sinogram, which is the pixel response of the detector for a single line through the object for all angles of rotation. And after which there is a computer phase where the radon transform is performed, and the tomographic reconstruction is computed. And this allows us to go from sinograms like this one to a stack of 2D slices, and therefore through a 3D volume of the sample. Now, one of the huge advantages, I would say, of synchrotron tomography is the possibility to work with a partly coherent light, X-rays. And this allows scientists to work in phase contrast. And this is also a very schematic representation of how it works. On the left, there are the X-rays coming in, and there are some objects here, which are just some circles, some disks. You see that 2 of them are opaque, and the rest is actually transparent to X-rays. So light materials like soft tissues or biological tissues. When the propagation distance between the sample and the detector is 0 or very short, you see that only the imaginary part of the refractive index is what gives the contrast. So we have only the 2 opaque disks leaving a significant image on the detector. On the other extreme, when you go too far from the detector, you have Fraunhofer diffraction patterns, and this is what is used, for example, in X-ray diffraction or small angle scattering. In between, there is an area of near field diffraction, where you can see Fresnel diffraction, where you can see fringes arising at the edges of the sample. So the transmission function of an object varies with propagation distance, and the projected image of the object develops fringes at the boundaries between disks and background. So phase contrast tomography can actually exploit these features to reconstruct and extract information on materials like these transparent disks that are actually transparent to normal absorption contrast tomography. And this is another picture of how it works. So the first row is a simple radiographic projection through a zebrafish embryo. This is very important for those of you who know, who work in biology or toxicology, or even for the development of new drugs. Zebrafishes are an animal model which is very important. The features that we see, I was saying, the first row is radiographic projection, the second row is normal absorption-based tomographic reconstruction, the third row is phase contrast tomography. So the features that we see in all these images are calcium earstones, which the fish is using for balance. And actually, this is dense, and therefore is the feature that we see in all the pictures. But the rest is all soft tissues. So soft tissues with very low differences in electron densities, which we cannot see if we operate a normal radiographic projection or absorption contrast. And what you see is that increasing the propagation distance, the edges become visible because we go towards a Fresnel diffraction regime. And with the phase retrieval, phase reconstruction, which was introduced in at the beginning of this century, we can actually reconstruct quantitatively the electron densities through these soft tissues. So one of the requirements to operate in phase contrast is actually to have spatial coherence. And X-ray sources, particularly when the source has a finite size, they are actually, they work as incoherent sources. The way this is optimized at synchrotron facilities is to work with very long beamlines and to reduce the size of the source. So in the table, I'm collecting information on other tomography beamlines in Europe, actually, compared with beats. And you see how the beamline length can reach actually 150 meters at high energy facilities like the SRF. But if we compare beats with Tomcat, CIRMAP, Elettra, and ANCA, we have actually a reasonable length. We are at 40, we can actually reach 43 meters of propagation from the source to the sample. The physical explanation, again, very simple, is here. A finite source size will project some blurring on the sample, and you can minimize this by taking the object very far away from the source or minimizing the source size. The problem for beats, due to the parameters of the storage ring as SESAME, are with the source size. So when we compare the source size with other facilities, we have actually a 2 millimeter, almost 2 millimeter full width half max source size, which represents a problem in terms of the coherence length of beats. So again, when we compare with facilities where we know phase contrast is possible, we don't reach enough coherence length for the application of phase contrast. So the solution for our case will be to work with a secondary source, which means that at 8 meter, 8.5 from the source, from the photon source, we will have primary slits, and which will be closed to a size which is smaller than the original source size. And this allows to produce a secondary source with enhanced coherence. Of course, we lose in terms of propagation length, and most importantly, we lose photons. I can actually show how we have calculated how much this flux reduction will be, and we know that we can work with that, live with that. But the important thing is that closing the slits from, say, 1 millimeter to 0.5, we will actually reach coherence length properties that are comparable with other synchrotron facilities, other tomography beamlines like Tomo at ANCA, where we know phase contrast is working. To conclude on this part, we said that there are two modalities depending on the energy requirements. So white beam versus monochromatic beam. White beam to deliver for fast applications, a high number of photons. Monochromatic beam to tailor the energy, and then Again, when we work in absorption and we just care for the flux, we leave the primary slits open and we work at high flux. When we want to use phase contrast and increase the coherence of the radiation, we close the primary slits that act as a secondary photon source. Now, to show very quickly the equipment of the beamline, this is the front end. This is currently in the design phase. We have launched the tender for the photon source. The rest of the equipment is being designed in a collaboration between INFN, ALBA in Spain. INFN is in Italy, ALBA is in Spain, yes, the SRF and Elettra in Italy, and of course SESAME. The front end includes absorbers and shutters for safety. And then right at the end here, there are filters, as I said, to tune the energy, the beam energy. The optics, right after the wall, we have a small hatch. We will have a small hatch with the main optical component, which is a double multi-layer monochromator. This is an example from the picture on the left, is a multi-layer from Tomcat. We have actually simulated and the working regime of this device for the angles that we need, the energies that we need. We will actually have 8 to 50 kiloelectron volt covered by these multi-layers with an energy bandwidth, a rather broad energy bandwidth between 2 and 3%, 2 different stripes, one with a tungsten coating and the other one with ruthenium, and different despacings as well to optimize the work at high energy tungsten and at low energies with a ruthenium coating. And the travel range must be, can be around 1 meter, 1 to 2. And with these parameters, we will actually cover the entire energy spectrum, energy range that we need for beats for our application. After the optics, there is essentially just a pipe, a shielded pipe that takes the beam to the experiment. And this is a diagram or a plot of the experimental hatch. This is a 14-meter long hatch where in brown you see granite. These are granite tiles covering 13 meters of the hatch. This is a very smooth floor that has to be prepared in a way that the equipment, the sample holder, the sample manipulator can be displaced along the granite to actually work with the different propagation distances between the source and the sample and the detector. As I explained, very important for phase contrast applications. And also we will use this to tune actually the beam size at the sample. I will show you how. This is the sample manipulator that we are planning to install, or the design that we hope we can adopt is a heavy-duty, high-precision sample stage, very well known at the SRF. So we have taken these pictures from ID19 and BM5 at the SRF. One important thing here is that the fact that it is heavy-duty, so it can support actually a high weight with relatively high stiffness. Also when you have tall samples like this, is that you can actually prepare a pile of samples and then scan them through the night, as it is shown in this picture. And this makes actually the use and partially the automation of the beamline very easy or easier. I was saying that we use this propagation to tune the beam size. These are snapshots of the beam at the entrance and exit of the experimental hatch, and you see that we can, for small samples, work close to the entrance where we have 30 millimeters of beam. For larger applications, where we need a large field of view, we can move the sample towards the end of the hatch and have actually 45 millimeters width of beam. So this defines more or less the sample size, the maximum sample size that we can have. And of course, for different applications, different resolutions and field of views, we need different detectors. And this is an example of 3 detectors that we are considering right now. There is on the left, A is a high resolution microscope, B is a microscope for the white beam, and C is a medium field of view detector. The field of views are shown here on the right for the different magnifications of the different microscope. You see that there is the 4th magnification, which is double, is present in the monochromatic and white beam microscope. The reason is that when you work with white beam, you cannot have the lenses in the propagation path of the X-rays, otherwise they will soon darken. And this is why the white beam microscope works vertically. So the X-rays are reflected down here by, after actually the light is reflected down here by a mirror after it is emitted by a scintillator, and then the objective is placed here vertically out of the beam propagation path inside a LED shielding. The different detectors will give different field of views and pixel sizes down to 0.4 microns for a target, a final target resolution, maximum resolution around 1 micron. All right, so this concludes the first part of my talk. In the next part, I will show you some of the applications and possibilities that are given by computed tomography, synchrotron computed tomography. Again, here is a schematic of the experiment with the sample stage camera producing 3D images. These can be applied for a variety of different scientific applications. We have material science and engineering to study light materials and alloys, or energy materials, or with in vitro with in situ chambers, materials under mechanical stress, to human health and biology and food research. We will see examples from musculoskeletal research, bone and dental, and soft tissue imaging. There is down here geology and environment. I will show some example on rock properties for soil characterization, for example. I will leave cultural heritage, as I mentioned, and archaeology to Dr. Kirsi Lorenz for the presentation after my talk. And then, of course, last but not least, microtomography can offer several services to industry and private sector, which I will not present, but you can contact us if you are interested regarding these possibilities. So starting with health and biology, this is an example with, these are actually different examples. There is on the left, there is a 3D scan of bioceramic particles used for bone tissue regeneration. This was a sheep bone. This was scanned ex vivo. So the animal was received surgery where these ceramic particles were implanted. After implantation, the bone, the animal was left to heal, and the bone regenerated after a while. The animal was euthanized, and the sample extracted and took to the Beamline in Berlin. And this was showing how exceptional contrast can be reached for materials with different densities to study actually the integration of the implant with the bone tissue. In the middle, there are animal samples that were collected from actually human donors, and synchrotron computed tomography was used to study demineralization of the animal. So this is caries research. This is very important for dentistry, the possibility to characterize the evolution, the morphology of caries and the evolution of animal demineralization. On the right, there are two examples from bone research. These are 3D reconstructions of a single trabecula. This is spongy bone from human donors again, and this is actually the fine scale vasculature inside cortical bone. So this is the dense bone of a human again, with in red vessels, and in white actually single cells trapped within the bone matrix. So the possibility to visualize these processes in 3D and without staining is very important for musculoskeletal bone and dentistry research. This is an example also from musculoskeletal tissue, but going towards softer tissues. This is an application on a salamander. Salamanders are a model for tissue regenerations because they are animals that can regenerate entire limbs when the limb is amputated. So this is an example showing actually the feasibility of synchrotron computed tomography to visualize single cells, the 3D orientation of single cells inside the cartilage and muscles of a regenerative salamander limb. And I wanted to show this because it has a very interesting comparison down here with conventional micro-CT, and astonishing or improved resolution that it is possible that one can obtain with phase contrast at a synchrotron facility. This was collected with 1 micron pixel size at the CIRMAP Beamline at Elettra, where I am actually now receiving a training these days. Another example from soft tissue imaging, this is liver tissue. This is fibrosis in liver. This image is nice because it shows the comparison with the standard for these studies, which is histological sections after staining. And if you compare the first line with the last one, you see how synchrotron computed tomography can actually reveal fibrotic tissue in a very similar, with a comparable quality than histological sections, without, first of all, without the need to stain and treat the tissue, without cryo-sectioning it, and most importantly, allowing a 3D visualization. So processes like this one can be visualized in 2D, but it is difficult to actually quantify, and perform a quantitative analysis in 3D. And this is allowed by phase contrast CT at a synchrotron facility. Another example from on soft tissue, but for neuroimaging, this is spinal cord. Again, a comparison with the histological sections and CT on the top with a much simpler sample preparation. It does not require staining, does not require cryo-sectioning, and the astonishing contrast here. This was performed at Tomcat at the Swiss Light Source, and the researchers were able to visualize in 3D microvasculature and actually the degeneration of these microvessels inside the spinal cord of mice at the onset of spinal cord demyelination in multiple sclerosis. Going from health towards biology, this is a study on biomineralization. Biomineralization is a process by which plants and animals deposit minerals inside bone, antler, this is an algae or corals, to improve their mechanical stability and their mechanical function. This is a work done on Red Sea algae, so algae collected from the Red Sea. Due to the specific environment where they grow, they need very high stiffness and resist to high mechanical stress. So this is the peculiar way, this helicoidal shape in which the algae deposits actually mineral to resist to the stress of the environment. So biomineralization means revealing structure-functional relations and actually understanding the mechanical performance of nature materials, but also designing new bio-inspired, lightweight, smart materials that can be fabricated following the principles observed in this in nature. Another example from entomology, so the study of insects. This can be used, synchrotron CT can be used to describe new fossils, fresh or even fossils, because we can see through amber or even rocks. This is, on the other hand, an example to study bacteriomes inside inside an insect. This is a leafhopper. CT can be used, synchrotron CT can be used to understand form and function of internal organs of insects. Now I'll move to food applications. These are two images from bread, and on the right there is a bean. Actually, the microstructural properties of food govern or determine the texture as well as the sensory attributes of food. So, for example, CT in this case can be used to tailor and control certain microstructural features inside the food without damaging the sample, without actually sectioning it. For the rest, I'm showing a couple of applications in materials science and geology finally. So these are light materials. These are scanned at the Beamline of the best synchrotron in Berlin. This is a foam of steel. These foams, as many of you might know, are very useful for the production of lightweight materials for the automotive sector, for example. Reducing the weight of vehicles improves, of course, the efficiency of the vehicle itself. So in this case, synchrotron computed tomography was used to study the nucleation of different phases in the metal phase itself, and as well as to control for the foam properties, so connectivity and defects in the foam, which at the end of the day will determine the failure properties of the foam, because defects act as stress concentrators. So at the end, it is where the fracture will start. So to control and check the fabrication process in 3D at high resolution is very important to actually determine the final mechanical property, mechanical performance of the material. This is an example from energy research. This is a fuel cell, and actually this is the only example I have of a 4D study. What does it mean? It means that the scan, the tomograph, is performed several times using very low exposure times. So a very short scan in the order of seconds. It can be down to 1 second or 2 seconds. And several 3D scans are performed while the fuel cell is operated. And the reason is that with operation, there is actually formation of water. So the water cell barrier is moved by the formation of water itself. And at a certain point, it becomes very difficult to analyze on moving images actually the evolution of the interior of the microstructural interior of the cell, and this is done to optimize, of course, the life of the cell and its performance. So the study, this study showed how it is possible to 3D register the scans to practically analyze the evolution of the water cell barrier in time without artifacts due to the movement of the material itself. And I think this is the final example I have. I'm sorry if this was long or boring. This is actually an example from geology. These are sandstone cores extracted in Iran, actually studied at the ID19 of the ESRF. On the left, there is a cross-section through the sample. I didn't put a scale bar here, but you should think of a couple of millimeters. This might be 3 millimeters in diameter. And going to B and C on the right, there is, these are snapshots of a quantitative analysis of porosity and tortuosity through the sample. This is very important because it can be CT data in 3D can be the input of numerical simulations to determine analytically actually properties about the rock, like its permeability as well as its mechanical properties, elastic modulus of or sound wave velocity. And this has implication for the understanding of the fluid dynamics in rocks, or for example, exploration studies on oil and gas extraction from shale from shale rocks. I hope that this covered a bit all the scientific applications of beads, and a little bit also the layout and the design that we will have. These are further information, further contacts, and I will leave now to Dr. Kirsi Lorenz on the cultural heritage and perspective. And I thank you very much for your attention, and I'm happy to receive your questions.
Thank you, Gianluca, for a very nice talk on beads, beamline, and applications of synchrotron tomography. Thank you very much. And now, I think we don't have any question personally to you, so we move on to the next